Good afternoon, everyone.
Who's Hans? Yeah.
Sorry?
Who's Hans? Hi.
Right. Good afternoon, everyone. Today is, as you know, the MATH2701 revision seminar for algebra, presented by me and Miles. Now, I will be doing groups and transformation groups, then we'll have a break for the sake of sanity, and then we'll be doing the projective plane and projective transformations with Miles. Alright, so first, 2026 peer mentoring. Remember how much of a smooth transition it was for first year, ending high school and starting your first time? Me neither, so help someone. Would anyone like to? Alright, groups. So, a group G is a non-empty set with an operation times defined onto it. They satisfy the four conditions. So if there exists an A and B in G, then A times B is also in G. Next, associativity. So A times B times C is equal to A times B times C. If anyone does not understand my handwriting, please tell me. I won't be offended. Now, the next... Oh, scroll. Sorry.
So just remember to go back and forth. So when you go out to bind the back and forth, press 1 and then go back to 2.
Yep. Okay. So next are the properties of groups. You remember from the assignment, hopefully, that the identity, when we have it in a group, it's unique. Do we all remember? Do I need to go through it again? Next, the inverse is unique, and if you invert the inverse, it's just equal to A. You can also find that A times B inverted is equal to B inverse times A inverse, because if you multiply each side by A times B, you find that this just equals the identity on both sides. Now, if you move on to the subgroups. Now, the subgroups are a non-empty subset H and G, where if H is a group and H is non-empty, close on the multiplication and close on the inversion, it is a subgroup. Every element of H has to be in G. So H must be non-empty, of course, and we must have closure under multiplication. And we must have closure under inversion. A corollary of this is that the identity must be in the subgroup, because if A and A inverse exists, and A times A inverse does not exist, that doesn't make any sense, right? Next, quotient group. Quickly. If we have a subset H and K in G, we define HK, which is subset multiplication, where we multiply every element in H by every element in K. Now, quotient groups, everyone's favorite part of this course, which is very intuitive. Now, K in G, that is a normal subgroup of G, if GK is equal to KG for all elements, little g in capital G. And it's written with this symbol, which makes sense to somebody. Now, if G slash K is this definition, or the coset of K in G, it is a group under subset multiplication. We call this the quotient group. We can think of this as dividing G into cosets about the cardinality of K, that many cosets. If you start thinking of this when it's a uncountably infinite or infinitely sized set for K, then it gets confusing, so don't stick to this metaphor too strongly. An example is Z slash 2Z. So we can split this into 0 and 1. This is equivalent to saying that if you have this set of even numbers, you can generate every integer by either getting 2z and adding 0 to every element, where we get all the even numbers, or adding 1 to every element. This would generate all of the odd numbers. Next is r such z is the half-open interval from 0 to 1. Because what we are essentially saying is that if we have a real number, we can split it into n plus the sum of k equals 1 to infinity of dk over 10 to the k. Do we all remember this definition of real numbers from analysis? Basically, this can fit inside this half-open interval, because every real number is the sum of an integer and some rational or irrational number between including 0 and not including 1. Okay, next. Homomorphisms. So for groups G and H, a map f from G to H is called a homomorphism if f of x equals f of xy equals f of x times f of y for all x and y in G. Please note, f of x and f of y, this operation is not the same as x and y. So for an example, we can have vector addition in x and y, but for f of x and f of y, we might have something else, such as matrix multiplication. So we cannot treat these operations as identical. If f is bijective, we call it an isomorphism, and we use this symbol for it. Next, rotation of hexagons which preserve x-intercepts and z6. This is a homomorphism. So suppose that we draw a hexagon. That looks like this. The only way to turn this hexagon into the same looking hexagon with a rotation is where the vertices, all two vertices, touch the x-axis. So notice how all of these rotations would be a multiple of 60 degrees. Now, if it's a multiple of 60 degrees, this is, in other words, just saying 60 degrees modulo 360 degrees, or just z6. In the same way that 1 plus 5 is 0 in z6, if we rotate by 2 pi, or 360 degrees, in a hexagon, we just get the same hexagon with no changes. It's fixed point-wise. Note that this is also isomorphic to the 6th roots of unity. Next, the transformations of vectors in Rn to the identity matrix. This is absolutely not isomorphic. So what we're saying is every vector in Rn is mapped to the identity matrix. Now, this condition is honestly quite trivially fulfilled because xy, that's another vector in Rn, as we know, closure under vector addition. So this is equal to the identity. F of x is also equal to the identity, and the identity is equal to the identity. So this is definitely not isomorphic, absolutely not a bijection, but it is a homomorphism. Next, smooth function Taylor polynomials. I hope this one's fairly straightforward. Smoothness is a requirement for a Taylor polynomial to exist. So if a function has a Taylor polynomial, it's smooth, and vice versa. This is something which I think was proved in 1241. Now, please consider the fact that if two functions have the same Taylor polynomial, they're just the same function. So that's why it's a bijection. Okay, so next, orthogonal matrices to linear isometry. So we can consider a isometry, a linear isometry. We know that isometries are of the form qx plus b, and for something to be linear, we can't have this translation component, so we just delete it from existence. What we're essentially saying is we can create a bijection where Q is the list of orthogonal matrices, and all of the linear isometries are qx for some orthogonal matrix. So this is a pretty clear bijection. Next, with addition as the operation, we can express z slash nz as congruent, I hope this is the correct symbol, from 0 all the way to n minus 1. Because if we have nz, so it's a multiple of n, we can generate every number by just adding a certain residue modulo n. So if we want to have, let's say, 5 generated with z/4z, we need to add 1, so 1 has to be an element. We want to include all the multiples of 4, so 0 has to be an element. We want to include all numbers of the form 4k plus 2, 4k plus 3, all the way to n minus 1. So that's why this is included. Okay. Do we have any questions? Anybody? Yep. Moving on to transformation groups. Now, B, at least I think that's a B, B of Rn is the set of all transformations, bijections from Rn to Rn on Rn. It is a group under composition. So we have the following subgroups. So translation. If you have a translation followed by another translation, we just get another translation. If we have an orthogonal map or a linear isometric map, then it is another group, because if we multiply 2 orthogonal matrices, Q1 and Q2, we'll have a third orthogonal matrix, Q3. Next, there is the group of isometries. Now, this can be generated by subset multiplication, where we include the translations and the orthogonal maps, because it's of the form qx plus b. Now, we notice that since q is an invertible matrix, we can also write this as qx plus q times q inverse of b. So, if we have q factored out, we have x plus q inverse of b, and then that multiplied by q. So we have an orthogonal map, and we have a translation. So every single isometry can be decomposed into an orthogonal map and a translation with this sort of algebra. Then is H, generated by the point reflections, the union of translations and point reflections. Now, if we have 2 half-terms applied, what we essentially have is negative x plus 2c for row of C. And then we have row B of x, and it's negative x plus 2b. Now, if we apply these together, then we have x plus 2c minus 2b, or if you use the other order, x minus 2c plus 2b. Please note that this also means that it's not abelian, it is not a commutative operation, because you can't just assume these two are equal. So, I don't think any of these are abelian other than the translations. So, do not assume that they're abelian with a commutative times or multiplication operation, because you'll get the question wrong if you do. Okay. Transformations on our end. Next, we have dilatations. Dilatations map lines to parallel lines. And then dilations are stretches, in a sense, of the form delta CR is equal to negative Rx plus 1 plus RC. This term might seem a bit nebulous, but the way to understand this is we can substitute C into this transformation, and then we have negative RC plus C plus RC. These two cancel out and it just becomes C. So that's the reason why we need the position vector C, because that is the vector that is unaffected by this operation. Translations are also dilations. It's fairly intuitive to think about, because if we have translations, shifting if we have parallel lines, shifting the parallel lines in a certain direction isn't going to change the fact that they're parallel. Next is similarities. So, similarities are including isometries and dilations and a lot of what we've been working on. Because it's a stretch, first of all, where basically we have a ratio r bigger than 0 and d of alpha of p, alpha of q, is equal to r times d of alpha p alpha q. Sorry, just p and q. That's the stretch. The next thing is that a similarity is the composition of a dilation and an isometry. So it's of the form x equals rqx plus b, where q is an orthogonal matrix and r is a positive real number. If you're wondering why r can't be negative, it's because we can simply just have q be a negative orthogonal matrix. The last one, and this is the most broad one, it's affine transformations and collineations. A collineation maps lines to lines. And it can be just very simply expressed in the form ax plus b. And the only real condition is that a is invertible. And square, of course. If the determinant of a is either 1 or negative 1, it is equiaffine. Now, the isometries, the dilatations, the half-turns, and the translations are normal subgroups of the similarities. And the similarities are a subgroup of the affine transformations, such collineations. Being temperamental, I apologize. I see. Okay, so let's C be a point in R2, and we define G is equal to all of the dilations around G, where R is any real non-zero number, and H is where it's all positive. Now, we can assume G is a group, and now we'll prove that H is a normal subgroup of G. First, the fact that it's a subset and that it's non-empty is clear. The fact that it's a subset is just the corollary of the positive real numbers being a subset of the real numbers. The closure follows from the fact that if you multiply them together, we just get RS, and RS is going to be another positive real number. If we invert it, then we just get R inverse, and since R is not 0, R inverse will exist. It is normal because when we have the multiplication of these two, it's commutative. And since delta CS times H is equal to H times delta CS for all delta CS in G, we can also consider the fact that the multiplication of the subset can be interpreted as equal. Now, clearly, we notice that if we multiply this dilation by the set H, sorry, the group H, we just get H again. And for delta CS, for delta CR, if R is bigger than 0, then we just get this. If it's less than 0, then we get all of the negative dilations. So the ones which are a composition of a positive dilation and a half-turn. If this is the case, then delta CS and H is equal to delta CR, where R is less than 0, all of the possible value, all of the possible dilations of that form. So this is two elements, because If r is bigger than 0, we just have h, and if r is less than 0, then we have a new element. So there's two elements. Next, so since we have two elements, our non-identity element times itself is 1. So we can consider that s is equal to 1 and negative 1, where we have a bijection phi which maps h to 1 and h prime to negative 1. Now, for every a and b in g slash h, it's pretty straightforward to show phi of ab is equal to phi of a phi of b. Next, plane isometries. So, every plane isometry is one of the following. It's either a translation, a rotation, a reflection, or a glide reflection. Now, a reflection about a line or a rotation of an angle theta around a point C is fairly straightforward, in my view at least. So we'll focus more on the glide reflection's critical details. So first, it is a composition of a reflection and a translation. By a vector parallel to L, this means that it fixes no points. Every type of plane isometry is either the product of an even or an odd number of reflections. So every translation can be written as a product of at most 2, rotations 2, reflections 1, and glide reflections 3. Plane isometries. Let's do this proof. We know a lot from the problem set. So, we know that sigma n, sigma m, sigma l is a reflection. Let's express this as just another reflection, sigma k. Now, when we do that, we can say on both sides we'll apply the reflection sigma l. Sorry, on both sides we'll apply the reflection sigma n. When we do that, from the properties of reflections, we know these two cancel out. Now, sigma m and sigma l are equal to sum product of two reflections. Now, there are multiple possibilities. If this is a rotation, these are concurrent at a point C. If it is a translation, then they are parallel. And if they're not parallel, then they will just be coincident. Classification of plane similarities. So, a plane similarity is exactly one of the following: an isometry, a stretch reflection, or a stretch rotation. If it's not an isometry, it has to have a stretch component by definition. So we can just think of this as the product of an isometry, or the product of a dilation and an isometry. Okay, generic position. Now we will say that P1 all the way to Pm, all of these points are in generic position if the vectors Pi minus P1 from I is equal to 2 all the way to M, if those are linearly independent. Now I'll go through this part slowly because it can confuse a lot of people. If L is equal to a line A plus lambda V, we say its direction L is a unit vector, and AB has the direction B minus A. We can consider the directed distance. Now, AB is equal to the distance from A to B, and if AB and L have the same direction, if they don't have the same direction, we write it as AB is equal to negative distance from A to B. Now, if A, B, and C are distinct, and CB over CA is equal to R, then this is the case, and we can actually map it with a stretch. This might seem a bit unintuitive at first glance, but you can visualize it. So we have a point C, and we have a point A, and we have a point B. And these are all joined by one line, which we will assume is actually straight on this whiteboard. Now, suppose that CB over CA is equal to R. So that means if you stretch the distances about C by R, then we are simply stretching CA by R amount. So we're turning CA into RCA, which is equal to CB. Now, some lemmas. So, if lines L and M meet at C and the directed angle from L to M is theta over 2, then sigma M sigma L is equal to rho C theta. If they are perpendicular, we have commutativity, and this would be equal to a half term. So, if we have the lines L and M, which are perpendicular, then we have a point here and a point here. Notice how if we reflect about L and then M, or about M and then L, we have the same half term. Next, a similarity without a fixed point is an isometry. It is either a translation or a line reflection. So, this part, the proof will not be included for the physical and mental health of everyone in this room, but you will have to take my word for it as a consequence. So, suppose that T is in the set R minus 1. Now, there exist points P and Q from L, A, B. So we have the point line L, which joins A and B, and we have the points P and Q. Now, suppose that AP over PB is equal to T. And AQ over QB is equal to negative T. It's a midpoint C that we consider. The midpoint, sorry, C is a midpoint if and only if AC over CB equals negative T squared. Now, if you really hate yourself, you can go to the lecture notes and go through it, but you'll have to take my word for it otherwise.
Sir, I have a question about the diagonal neutral. AQ over QB is negative, so Q should be on the right side of B.
Whoops. All right. Collineations. Suppose the transformation alpha from Rn to Rn is a collineation. This maps the images of collinear points, which are always collinear. So lines map to lines, essentially. If the lines L and M are parallel, alpha L and alpha M are parallel. And if M is the midpoint, so alpha M is the midpoint of alpha A and alpha B, then if M is the midpoint of A and B, alpha M is the midpoint of alpha A and alpha B. This can be generalized to say that if there is a point A, C, and B such that they're all collinear and C is between A and B, if AC over CB equals R, then A prime C prime over C prime B prime is equal to R. So the stretches are uniform in summary. If there is a midpoint, R is equal to a half, and it will be the midpoint later on, but we can also think of it as if R is a quarter here, R will also be a quarter here. Next, all similarities are collineations because dilations and isometries are all collineations. Now it is worth noting that the form alpha from x to ax plus b for some b in Rn and invertible matrix A, it's very useful for proofs with collineations. For an example, if you want to prove the midpoint property, you could just say, we have the points A, B, the direction, the position vectors are A and B, and the position vector of the midpoint is M, or the average of the vectors A and B. We can simply write that A of M plus B is equal to A of... Now, after some algebraic manipulation, you will find that this is just equal to the average of alpha A and alpha B. So, if we just have it in the form AX plus B, where A is an invertible matrix and B is a vector in Rn, we have a much simpler way to prove a lot of critical properties of collineations. All right, corollaries. So, if alpha fixes only n-1 collinear points, it is a product of two reflections. If alpha fixes n non-collinear points, it fixes the hyperplane containing all endpoints pointwise. This would mean that alpha is a reflection, since it fixes the hyperplane. If alpha fixes n plus 1 points, that's just the identity. Do you have any questions before we move on to the example? All right. Let alpha be an affine transformation of R2. Find a similarity tau such that tau inverse alpha is equireal. Write down an affine transformation alpha of R2 which is equireal and is not a similarity, including a brief proof. Would anyone like to have a hand at seeing how to solve any of these questions before I proceed? Anybody? Right. That's such an active class. Right. Alpha of x is equal to ax plus b. That's a collineation. Now, the determinant is positive or negative, but we'll get the absolute value. So d is equal to the absolute value of the determinant. Now, we can get tau inverse to be a dilation with a scaling factor of 1 over d, because then A over D will have a determinant of either 1 or negative 1, and this would make it a equiaffine transformation. Next. If it is equireal, then we can create a matrix where the eigenvalues multiply to be equal to 1 or negative 1. For simplicity, we'll just choose 1 for our construction. The simplest case I will bring forth to you is just where the eigenvalues are lambda 1 and lambda 2, and these are equal to 2.5 respectively. Now, if we construct a diagonal matrix 2, half, 0, 0, we define this transformation. Then we notice the determinant of this is 1. But if we multiply this matrix by literally any vector in R2, then we get to 2x1 equals x2, half x2. Sorry, x1 maps to 2x1 and x2 maps to half x2. So it's understandable why this is a determinant of 1, because if we have a 1 by 1 unit square, this maps to a rectangle of sides half and 2. 2 times half is equal to 1 times 1. Fair. But this isn't going to preserve any shapes. Look at how this square just gets contorted by this. These two shapes don't look very similar anymore, do they? All right. Unless we have no questions, we can move on to the break and projected geometry after. Does anyone have a question? Right. I guess we'll have a break of 10 minutes. Sorry. I know. I really loved how active everyone was, by the way. I really felt like it was more of a conversation than a lecture.
You would make a great lecturer.
I'm tired. I'm doing this while sick. My throat is dead. By the way, have a drink of water during this. It's trust me. You should do it on the blackboard just to really cement your status as an old grizzled lecturer.
7 minutes. And this screen. Okay.
Sorry? I guess I'm famous now.
You press 1, it goes to the choose the sides. So whenever you use the blackboard, preferably use the blackboard over there because it'll capture better. I think.
That's the one.
You can use this one. You can also use that one because it'll just try. If you want to tracking your so just make sure when you're writing the blackboard, try to have it on scene 1. So scene 2 is the slides. So when you go to the slides, you go through scene 2. You just go from scene 1 to scene 2.
I mean, I have to the slides.
It should.
Do people want me to
If I was
email
on-
the PowerPoint?
Yeah, it's tracking you.
Is everyone okay? Everyone looks like they're gonna have a mental breakdown. You realize it's just a uni class, right? You're not gonna die. It's not like you're gonna get beheaded if you fail.
This is the worst course I've done. We don't fail this. If you fail this course, actually no, engineering is
Sorry.
worse. If you fail this course, bro, it just is over. You have to do it. Like so afraid of failing. I probably won't fail, but like, I'm gonna take my health's gonna take a
I
hit.
feel if I study properly, I can do it, but I'm still scared.
No, but to be fair, isn't it that much of a shame if you failed in the first year? If I failed in the second year, like, oh my.
You fail and you can do it again. I don't want to do it again. I don't want to sit through algebra again.
The second moment method,
What is it?
it's a technique in probability theory to show that a random variable has positive probability that it's positive. So it's like,
So it has negative
so
probability that it's
so
negative?
there can be a 50% chance that your variable is positive.
Wait, does anything have a 0 probability?
Oh wait, things that don't happen.
Oh, that's what. Sorry?
Things that don't happen.
I think so.
Are there things that have a 0 probability?
You can do,
Are there?
Yeah.
Like what?
you can do particle and then the negatives cancel out, right? And then it makes sense after that.
Sorry? It's just like EMX is equal to. Wait, is the microphone on? I want that better weakness. Miles trusted me so little to not say anything stupid. You literally had a recording sign in case I said something really funny. Jordan is the original reference, wasn't it?
I've seen like the charger.
Like, I think I said at one point that the well doesn't owe you anything or something. I'm not sure. Oh, well, my mouth says it. Oh, because I didn't say any swear words. Did I even swear at all? Seriously, it's like. How is everyone so quiet? Did we not believe that a square is distinct to a rectangle? Well, that's the projective geometry. No, I know they're not logically the same, but just look at them. As a point of a similarity, the shapes are similar. Did you know that the circle is the same shape as a hyperbola?
I'm not a math student. I'm just sitting on it because Brendan. I had it just before this. Anyways, as in classes.
Aren't you used to the clattering noises? Aren't you used to the clattering noises?
Oh, yeah. I'm taking electronics term 1. I want to take advanced probability and stochastic. Turn to take control.
Sorry. Is this recording?
I take it easy right now.
Sorry. I mean, to be fair, no one
Honestly,
is.
it's very fruit. It's pretty poorly run.
My record is not a problem.
No, but you can, like most people, you can get 100. But it's not.
You just have to deal with the variables.
Yeah. And the problem, like the final doesn't assess your actual understanding,
Yeah.
which is like.
If you remember it's not time. Like, do you remember how to do this?
Yeah, it's stupid. I mean, I didn't memorize the thing, but I still ended up doing it pretty well. But if you memorize it, well, then there's no excuse for a contact.
But you said I didn't match you.
Yeah, if you're a math student, I mean, it's like it's a lot of
Look backward
for
from it.
control theory. A lot of differential equations.
Not look forward to it. Look back.
And if you go into the higher level stuff, there's nonlinear control, which is of course stochastic control. I think that's also the thing. Or advanced.
It's
You
so-
want actually like single class.
Drink some water.
Sorry.
Drink some water.
Drink some water. It's not there.
Then it's fine. It gets better. The more you lecture, it's fine. Do it over.
I think like advanced DSP is a stats course disguised as a direct course. Yeah, it's optimization on the simple side. Realizing that.
Sorry. Do you have attendance for?
Just enough. My mind gets loud. I'll just take I don't remember it.
It's okay.
It's well.
Is this working?
It's just physics.
Am I audible? Am I audible?
Yes.
Okay. It is time for the projective plane then. Projective geometry is the art of trying to build intuition and then just sacrificing it completely. So, R2 has a bit of a problem. Normally, if we just have some arbitrary pair of lines, they will intersect at exactly one point, assuming that the lines are distinct. However, if we have two parallel lines, then obviously they're just going to go off into infinity, not intersecting anywhere. So, simply with the complex numbers, we just invent some arbitrary position and say that's the answer. And the set of all of these imaginary positions is known as the ideal line. And then we can say that any two distinct pairs, any two distinct edges intersect at exactly one position. And we call the set of normal points in R2 combined with this ideal line the projective plane. So, firstly, we define RP1 to just be this magical line off at infinity, and then we can define RP2, the real projective plane, is equal to R2 union the imaginary line. We can then just generalize this definition recursively, and we have Rpn is equal to Rn combined with the with some sort of abstract projective space. So for instance, for Rp cubed, the ideal area is basically a plane. Fortunately, in this course, we only have to care about RP2 because everything gets even more cooked when we increase to higher dimensions. So now that the projective plane is more than just 2D coordinates, we have to increase the space for representing points. Do we have a whiteboard eraser? So the logical choice is to extend this into 3 coordinates. However, now we arise at a problem in that the R2 is 2-dimensional and the ideal line is 1-dimensional. So now when we try to combine those into some 3-dimensional space, we're going to end up with a bunch of extra wasted space. So what we do is we define points in R3 as x0, x1, x2, and we write them with these square brackets to denote that what we're actually talking about is equivalence classes instead of points themselves, because we say that they are equivalent to any non-zero scalar multiple. And then we just declare that the point 0, 0, 0 doesn't exist, because otherwise this equivalence relation is no longer an equivalence relation. And so now we can relatively easily create some sort of mapping from ordinary points to projective points by just saying that xy maps to 1xy. This then leaves us with the choice of points on the ideal line being anything where the x0 coordinate is 0. Notice this means that with ordinary points where x0 is non-zero, we basically have 2 degrees of freedom, because we can divide the whole thing by x0 to normalize it into a form where the first coordinate is 1, and then these next 2 parameters are arbitrary real numbers. Whereas for ideal points, we only have 1 degree of freedom, because it's entirely about the ratio between x and y here. We can try to normalize this, for instance, setting x to 1, but then we have to deal with difficulties with x possibly being 0. So that gives us an easy way to define positions in RP2. We can also visualize this another way as visualizing points in the projective plane as subspaces of R cubed, where we have some point defined by an equivalence class in homogeneous coordinates. This is equal to the span of vectors x0, x1, x2. You can see by the definition of a span that this works with the fact that we're defining scalar multiples to be equivalent, and this will turn out to be useful later once we define lines in RP2. And note that with this definition, we now no longer have any real distinction between ordinary points and ideal points, so we can treat them as the same things. So you probably recognize that in R2, we can define any line as an equation of the form a plus bx plus cy is equal to 0. And because we're representing ordinary points as 1xy, but with scaling, we can just multiply the first coordinate by x0 and replace this with a, x0 plus b, x1 plus c, x2 is equal to 0. And this is how we define a line in the projective plane. Note that this is also the equation for defining a plane in R cubed. This corresponds to the fact that when we are representing the real projective plane in R cubed, a line is just a 2-dimensional subspace. Indeed, it's the two-dimensional subspace that is spanned by any two distinct points on that line. Yes, and with this definition, we can now get the actual coordinates of a point that is on the ideal line for any given two parallel lines, because if we have two parallel lines, we'll be able to represent one of them as a plus bx plus cy is 0, and one of them will be a prime plus bx plus cy is equal to 0, notably both with the same values of b and c. That's just how gradients work. And this means when we translate them into this homogeneous form for projective lines, we will have the solution 0 c negative b, which you can find if you just substitute that in, because the a term here, which is only distinct for distinct parallel lines, becomes multiplied by 0. Okay, so here is a problem from one of the problem sets. We are given a series of conic sections, and we have to calculate their equations in the projective plane, and then identify where they intersect with the ideal line. So first what we need to do is map all of these points in R2 into points in RP2. And because we have the fact that 1xy is equal to lambda x lambda y, we have that if the equation holds for x and y, it must also hold for lambda x and lambda y. So we need some way of mapping points to real projective points that preserve this scaling. So what we do is we map x into x1 on x0, and we map y to x2 on x0. And that will guarantee that this condition still holds. So for the first one, x squared is equal to y. This just simplifies to x1 on x0 squared is equal to x2 on x0. And so x1 squared equals x2 x0. And so now this is an equation for a parabola in the projective plane, and to find where it intersects with the ideal line, well, the ideal line is just the set of points where x0 is equal to 0. So we have x1 squared is equal to 0, and x2 can be any arbitrary value, but because we only care about points up to scaling, we have that the only solution is 0, 0, 1. So you could sort of think about this as saying that as the parabola goes off to infinity, it eventually becomes parallel with a vertical line, but intuition is kind of something you have to abandon at some point for the projective plane. Does anyone have any questions about how we got up to here? Okay, in that case we can proceed with the rest of the conics. But first it's useful to see a trick we can use for not having to go through this substitution every time. For polynomial expressions, such as all of the examples here, if we just substitute x becomes x1 and y becomes x2, we can then just multiply each term by x0 until all terms have the same degree. And if you look at the polynomial, you can see that that just happens with how division will work. However, in practice, it's much nicer to use. So for instance, in this example, we would end up with x1 squared is equal to x2, and then because this term has degree 2, this one has degree 1, we just multiply that by x0 to give them all the same degree. So in the next example, we have a some sort of ellipsoid. So x squared on a squared plus y squared on b squared is equal to 1. And if we use the trick for homogeneous polynomials, we get x1 squared on a squared plus x2 squared on b squared is equal to 1. But now, since this 1 has degree 0, and we need to have degree 2, that just becomes x0 squared. So then, when we try to find points on the ideal line, we just replace x0 with 0. And hopefully you can see that since both of these terms are guaranteed to be positive, well, non-negative, the only solution is 0, 0, 0, but that just isn't a point. So we find that an ellipse doesn't intersect with the ideal line, which makes sense if you think about the ideal line as being off at infinity. An ellipse is going to be some bounded thing. It won't intersect anywhere. And then the... Oh, that camera has moved away. It's ignoring me. The final equation was a hyperbola. So x squared on a squared minus y squared on b squared is equal to 1. Again, we can just substitute in and make the degrees match up. We end up with x1 squared on a squared minus x2 squared on b squared is equal to x0 squared. And then again, setting x0 to 0, we have x1 squared on a squared is equal to x2 squared on b squared. And by inspection, we can see that the only solutions to this are going to be 0, a, b, and 0, minus a, b, again up to scaling because we're using homogeneous coordinates here. And if you think about a hyperbola, it's going to have 4 distinct rays going off to infinity. However, they're going to come in parallel pairs. So you have the hyperbola like that. This ray here is basically parallel to this, and similarly, this is parallel to this. And so it makes sense that we have 2 intersections with the ideal line. Yeah. Okay, so now we have any questions about the intersections of conics? Okay, now we have one of the most bizarre properties of the projective plane, which is duality. So you've noticed that both a point and a line in the projective plane can be just described by three real numbers, because a point is the span of x0, x1, x2, and a plane is just the set of points that satisfy a0 plus b x1 plus c x2 is equal to 0. Notably, both of these are just equivalent up to scaling. So it seems as though there is some sort of isomorphism between them. And indeed there is, that is the dual. We also have that we have symmetry in that in R2 we have every pair of points defines a unique line, but we don't necessarily have that every pair of lines has unique intersection points. Now that we're in the projective plane, every pair of lines does have exactly one intersection point, either an ordinary point or a point at infinity. So now we can try to formalize that symmetry by defining the dual. First we need to define the orthogonal complement, which is a function that operates on some subspace of Rn, and it's just the set of vectors which are orthogonal to every vector in the original subspace. For instance, if our original subspace, if we're thinking in R2, and our original subspace is let's say the line y equals x, so this is W, then the orthogonal complement is just going to be every vector that is orthogonal to every point on W, which is just going to be the line y equals minus x. And you can observe that in Rn, the dimension of the orthogonal complement of W is going to be n minus the dimension of W, assuming that W is a complete subspace. In R cubed, which we're considering as like the same as RP2, you'll notice that 3 minus 2 is 1, and 3 minus 1 is 2, which means that if we take the orthogonal complement of a point, that will give the orthogonal complement of a projective point, which is a one-dimensional subspace, we get a two-dimensional subspace, which is a projective line. Similarly, if we take the orthogonal complement of a projective line, which is a two-dimensional subspace, we get a one-dimensional subspace, which is a projective point. So we define this operation as taking the dual. And taking the dual does have some nice properties. So if we have the span of a point x0, x1, x2, i.e. the projective point with homogeneous coordinates x0, x1, x2, then its dual is just going to be the line. Actually, it's probably easiest if we rename this. If we have a projective point A, B, C, then its dual is going to be the set of points ax0 plus bx1 plus cx2 equals 0, because this is basically the equation for a dot product. It comes out of the other definition for a plane in R3. Similarly, if we have some line, a projective line defined by ax0 plus bx1 plus cx2 its orthogonal complement is going to be the projective point ABC. This means that for any point or line, any projective point or line, if we take the dual twice, we obtain the original thing. Okay. And finally, we come to the most important property of duals, which is the principle of duality in the projective plane. If we have some line L with a point P, then when we take their duals, we are going, P is going to become a line, and L is going to become a point. And the dual of L is going to be incident with the dual of P, if and only if P is incident with L. You can actually just see this from the definitions. So we define L as the set of points where A x0 plus B x1 plus C x2 is equal to 0. And so by definition we have that P satisfies this, and that the dual of L is going to be the point A, B, C, and so this is going to, because P is on L, if we say that P is equal to Q R S, then Q x0 plus R x, sorry. By definition, since P is on L, AQ plus BR plus CS is equal to 0. And now the dual of P is the line Qx0 plus Rx1 plus Sx2 is equal to 0. And if we substitute in the dual of L into this equation, we end up with QA plus RB plus SC is 0, which we already know is true since P is on L. Does everyone understand how we're defining duals? Okay. And that brings us to the principle of duality, which is that in RP2, if we have some statement involving points and lines, then if we swap the words points and lines, and possibly swap a few other words due to like a point being on the line becoming the line being on that point, then the truthiness of that statement is conserved. This makes it a lot easier to prove certain theorems, as we'll see at the very end of the slides. It's kind of messy defining the principle of duality in this way, because we can have a true statement about 3 points being collinear, for instance. So if we have A, B, C are all on L, if we take this definition as is, the dual of this statement is that the lines A prime, B prime, and C prime are collinear, which doesn't really make sense. However, we can replace that with concurrent, and we end up with the lines, the lines A dual, B dual, and C dual are concurrent at the point L dual. And there are ways to formally define this swapping words around, but it gets messy, and that is not part of the course. So, here's an example from a past exam where we have to find the dual of this statement. So, the first thing we have to do is find the dual of each individual item. So we have P1 is 100. So that is an ordinary point since x0 is 1, and its dual is therefore the line defined by x, well, we have 1 times x0 plus 0 times x1 plus 0 times x2 is 0. That's just x0 equals 0, which is the ideal line. And then we have, for instance, we can take the duals of all those points the same way. For instance, P4 is equal to 1, 1, 1. Therefore, the dual of P4 is equal to the line, which is the set of points where x0 plus x1 plus x2 is equal to 0. We also need to take the dual of each statement in this statement. So instead of tau mapping collinear points to collinear points, tau is now a bijection that maps concurrent lines to concurrent lines. And then in the final statement, we just have that if tau fixes the lines P1 prime, P2 prime, P3 prime, and P4 prime, then it is the identity map. So here we just calculated all of the duals. We just get 4 distinct lines. They're like the ideal line, the x-axis, the y-axis, and then this one other random line here. And we are claiming that if we have some bijection that preserves concurrent lines, that fixes all of these lines, it must be the identity. And so we obtain that as the dual of the previous statement. If we assume that the previous statement is true, which it probably is, that's a proof left as an exercise for the audience. So if that previous statement is true, then by the principle of duality, we have just obtained another true statement. Any questions about duality? Duality is probably the most bizarre part of projective geometry. Okay, now we're moving on to projective transforms, which seem a lot more reasonable than most other projective geometry things. So, a projective transformation is just any linear transformation on the subspaces that we're representing projective points by. So, if we have some invertible matrix A, note that A is dimension 3, for the projective plane because our homogeneous coordinates are three-dimensional. And if we have some matrix A, this gives us a transformation tau of some subspace is equal to the subspace AX. Okay. So this means that if we have any linear isomorphism from an n+1 dimensional space to itself, that will give us a projective transformation just by definition. And we are claiming that this set of projective transformations is a group. So firstly, we note that the projective transformations are identical up to scaling because of the definition of a span, because we have AX is equal to lambda AX for any non-zero lambda. So this means that the set of projective transformations is isomorphic to the set of invertible matrices modulo the non-zero real numbers. Again, this means that we're kind of doing all of the transformations and coordinates in a space one-dimensional higher with redundancy, which is kind of messy but useful. So the claim is that this projective transformation space is a group, and we kind of just have this from the fact that tau A multiplied by tau of B is just tau of AB. Assuming B's are both invertible, that will mean AB is also invertible. So we have closure under multiplication. And from here, we also get the identity element of the projective group is just tau of the identity. And we also get inverses from here. Tau of A inverse. Okay. We also see that there is a lot of similarity between affine transformations and projective transformations. So if we have any affine transformation on R2, we can turn that into a projective transformation on RP2 that fixes the ideal line. So if our affine transformation is tau maps x to ax plus b, where A is a 2x2 invertible matrix and B is a two-dimensional vector, then we can get a projective transformation that is defined with A in the bottom right corner, B here, the top left corner 1, and these two positions 0. Is that the right shape? And so if we multiply this by an ordinary point, 1 xy, this gives us 1b plus x times 0, and then like the first column of A plus y times 0, and the second column of A, which is the same as, well, the same as the projective version of tau of x. And if we have this multiplied by any ideal point, 0, x, y, then the first coordinate is going to be 1, 0, 0, dot 0, x, y, which is going to be 0, and so it fixes the ideal line. And this mapping from affine transformations to projective transformations preserves multiplication and inverses. Proof is left as an exercise to the audience. So, now we are dealing with a projective transformation. We have a transformation defined by the matrix A is equal to 1, 1, 1, 2, 3, 4, 3, 4, 3. And we have L is the ordinary line defined by x minus 2y is equal to 1. So we want to find pi of L, pi of the ideal line, and the preimage of the ideal line. Okay, so first we need to do the standard homogenization. So we have x1 minus 2y to x2 is equal to 1, and then in order to have this also degree 1, we multiply it by x0, and we can parameterize this in terms of two variables we'll call mu and lambda by having x0 equals to lambda, x1 is equal to 2 mu, and from that we get x2 is mu minus lambda. So now we can parameterize this as L of mu lambda is equal to, well, the x0 coordinate is going to be 2 lambda, that should be 2 mu, 2 mu, and then mu minus lambda. So now, when we apply the transformation on this parameterization, we have linearity. So we have pi of L of mu lambda is equal to 2 lambda, first column of A, plus 2 mu, second column of A, which is 4, plus mu minus lambda, third column of A. And if you do the arithmetic, you have that parameterization there. And then you can turn this into a Cartesian equation in homogeneous coordinates by just taking the cross product like it's R3, and that gives you a line in homogeneous coordinates there. So to get an ordinary line from that, you just set x0 equals 1, and so we get the ordinary line x plus y equals 3. And so we have that pi of L is the set of points such that x plus y is equal to 3. Does everyone understand how we got to there? Because now we apply a similar technique to the ideal line. So we can define the ideal line as the span of any two unique points on the ideal line. So we may as well pick 0, 1, 0 and 0, 0, 1. And now the image of pi, the image of the ideal line under pi is just going to be the span of A multiplied by each of these points. So we have that pi of L infinity is equal to the span. And because we've chosen these as just our elementary vectors, doing the matrix multiplication is easy. So we get it's the span of 2, 3, 4, and 3, 4, 3. And again, you can convert that back into a Cartesian equation if you really want to, but we are not going to bother with that. And finally, to take the pre-image of the ideal line, that's just going to be the set of points such that after we apply A, our first coordinate is 0, i.e. the set of points such that this top row of the matrix dotted with the point 2, 3 dot x0, x1, x2 is equal to 0, and that is just by definition the line that we want, so that corresponds to the set x0 plus 2x1 plus 3x2 is equal to 0. Okay. And note that this is now an ordinary line, so our transformation here is sending an ordinary line to the ideal line, and it's sending the ideal line to an ordinary line, because these two vectors are both ordinary points. Okay, so a projective collineation is just a projective transformation that is also a collineation. And the claim is that every projective transformation formed by a matrix is just a projective collineation, and vice versa. So we have that every transformation in the projective group preserves collinearity, which is very useful for various proofs, as we'll see at the end of this. Okay, so now we need to define projectively equivalent. Similarly to how we've defined congruent or similar figures, two figures in the projective plane are projectively equivalent if there is a projective transformation that transforms one of them into the other. And we have a claim here that all quadrilaterals are projectively equivalent to each other. You can prove this by proving that they're all projectively equivalent to the unit square, and then proving that projective equivalence is transitive. Similarly, we also have that all conic sections are projectively equivalent to each other. Proof of these is left as an exercise to the audience. Alright, now we are going to move on to the most bizarre example of the projective plane path, which is proving the dual of de Sigel's theorem. So, this is going to involve a lot of lines. So, we have 6 lines, L prime, we have let's move that label there. L prime, M prime, and these intersections form a line L, and finally we have one more pair of lines, it's N and N prime. And if you think that diagram looks messy, we're going to draw 3 more lines on it. So we have L1 is at the intersection of L and M, and L prime and M prime, which is going to be somewhere off here. So this is L1. Actually, I think I'll use a different colour here. So this is, is that too bright? Okay. Okay, we have L1 goes through those intersection points. L2 is for L and N. Okay. There. And L prime and N prime. There. And then L3 is M and N, and M prime and N prime. And if I drew the diagram correctly, which I didn't because I can't draw straight lines, then L1, L2, and L3 should be concurrent, except just pretend they are there. So, this diagram is kind of messy, as you could think. It's also not the easiest thing to just visualize from that statement. However, what we can do is apply a projective transformation on it, because we're only dealing with like concurrency, collineation, and points being on lines, then the statement will still be true under a projective transformation, if it is true here. And because it's bijective, that applies both ways. So we take this line L, that all of the intersections are on, and we map this to the ideal line. So now, because L and L prime intersect at the ideal line, they must be parallel. That is parallel to that. Similarly, because M and M prime intersect at the ideal line, they must also be parallel, and same with N and N prime. This simplifies our diagram to this triangle thing. So now we have a triangle here, where so the lines of the blue triangle are L, M, and N,
and the lines of the red triangle are L prime, M prime, and N prime. And so now we have two similar triangles here, and we want to show similar triangles with parallel edges, and we want to show that the lines that you draw through AA prime, BB prime, and CC prime are all concurrent at some point. Now, if you think back to the classification of similarities, the only ones that preserve parallel edges are dilatations. So this means that the transformation from the red triangle to the blue triangle is either a translation or a dilation. If it's a translation, then AA prime, BB prime, and CC prime are all parallel lines, and so they will all be congruent at some point. They will be concurrent at some point on the ideal line. Otherwise, there is some stretch map delta CR such that, let's just denote it delta for short, such that we have delta of A equals A prime, delta of B equals B prime, delta of C equals C prime. And remember, one property of stretch maps is that when we have some property like this, then C is on the line. Okay, we shouldn't use C. Okay, the stretch is centered around D. So this implies that D is on the line A prime. Similarly, D is on the line B prime. And D is on the line C prime. And this implies that, by definition, that D is the point where each of these three lines are concurrent. So that was a bit of a messy explanation, but that is not scrolling anymore.
It was just the last slide.
Oh, I was trying to scroll up to the previous.
That's all right.
Okay, that is not first now. So now we have proven that statement there, which is the dual of the Side-Use theorem, and by the principle of duality, that also suffices as a proof of the Side-Use theorem. Note that the Side-Use theorem is normally used in just R squared. So now we've taken some problem from R squared, transformed it into something in the projective plane, taken the dual of that, and then we've simplified it with some projective transformation, and all along the way, each of the steps we've done has preserved truthfulness. And so the projective plane lets us prove useful statements about R squared that would otherwise be more complicated to prove. So, does anybody have questions about the projective geometry path? Okay, in that case, we are done. Brendan will be hosting the analysis half of this revision session 2 to 4 p.m. tomorrow. Thank you for coming.
Can I get you all to scan the QR code, please? Put that up there. I'm sorry, MathSoc's too broke to have pizza. There's a better society that I won't name that has pizza. Yes, thank you to my listeners. Great work, guys. Solid work.